Okay, morning we discussed up to conductometric titrations. Next one, potentiometric titrations. In potentiometric titrations we have acid base titrations, redox titrations and precipitation titration. So acid base titration. So acid base titration, and simultaneously I will explain determination of pH also. We have the expression for pH. What is the expression for pH? Minus log concentration of H plus. Minus log concentration of H plus. So we have to select an electrode reverse to H plus ion concentration. We have to select an electrode reverse to H plus ion concentration. How many such electrodes are there? We have 3 such electrodes. One is hydrogen electrode, quinhydron electrode and glass electrode. All those 3 are reverse to hydrogen ion concentration. All those 3 electrode potentials depends on hydrogen ion concentration. If you use hydrogen electrode, what is the expression for pH? What is the expression for pH? E cell minus E cathode by 0.059. This is the formula for pH if we use hydrogen electrode. If cathode is saturated calomel electrode, we get 0.242. If cathode is standard hydrogen electrode, what we get? 0. Okay, then. Cell potential we get by using potentiometer. Okay, we have to take hydrogen electrode in the solution whose pH we want to determine. We have to take hydrogen electrode in the solution whose pH we want to determine. As single electrode potential we cannot determine, we have to combine hydrogen electrode with another reference electrode. That may be saturated calomel electrode or standard hydrogen electrode. Okay. Next, what is the expression for E cell by using hydrogen electrode? The expression for E cell, if you bring this left side plus, we will get 0.059 into pH. So that is E cathode plus 0.059 pH. This is the expression for cell potential. So if you take acid base titration, while we are adding NaOH, what happens? pH of the solution, right, increases. On adding NaOH, what happens to pH of the solution? Increases. pH of the solution increases, so therefore E cell also increases. On adding NaOH, pH of the solution increases, so cell potential also increases. In the beginning, slow increase is observed, and at end point, sudden jump in the potential is observed. Sudden jump in the potential is observed at end point. Okay. So if you plot a graph between E cell versus volume of NaOH we are adding, we will get a graph like this. Sudden jump in the potential is observed near end point, or we may get by taking what? Delta E cell by delta V versus volume of NaOH. So from peak we have to take a straight line towards volume axis, that gives end point. So end point get clearly by taking delta E cell by delta V versus volume of NaOH. So at end point, delta E cell by delta E value is maximum or greater than 0. Whereas for delta square E by delta V square versus volume of NaOH, if you take, which type of plot we will get? That is delta square E by delta V square value is 0 at end point. Delta square E by delta V square value is 0 at end point. Similarly, delta pH by delta V versus volume of NaOH, also we get same graph. Delta pH by delta V versus volume of NaOH. Here E cell is changing since pH changes, right? So delta pH by delta V versus volume of NaOH, also we get same graph. This is by using hydrogen electrode. Okay, this is the formula you remember. E cell minus E cathode by 0.059. From that E cell value, this is the expression. So as pH, on addition of NaOH, pH increases, cell potential also increases. Next one, if you take quinhydrone electrode, and quinhydrone electrode. What is quinhydrone electrode? It is a 1:1 mixture of, it is a 1:1 mixture of what? Quinone and hydroquinone. Quinone and hydroquinone. Quinone, if you indicate with Q, hydroquinone is indicated with QH2. It is an example for which type of electrode? Redox electrode. Okay, it contains both quinone and hydroquinone, both are present in the solution. So that is called redox electrode. What is the formula for pH? And if you use quinhydrone electrode, the formula is 0.457 minus E cell by 0.009. So they may provide E cell value and they may ask you to calculate pH. And they may provide E cell value, cell potential value may be given to you. They may ask you to give pH. Our pH is given, we can calculate E cell. And from this, what is the expression for E cell? If you bring this E cell, minus E cell to left side plus E cell, we will get. So 0.457 minus 0.059 pH. 0.457 minus 0.059 pH. So therefore, on adding NaOH, what happens? And pH increases, negative value is increasing. That means cell potential decreases. Sudden decrease is observed at end point. Sudden decrease is observed at end point. So if you take acid base titration, what happens on addition of NaOH? On addition of NaOH, pH increases, so cell potential decreases. Okay, at end point sudden jump is observed. Only this graph is different. And E cell versus volume of NaOH. E cell versus volume of NaOH. We'll get a graph like this. Okay, here cell potential increases, but here cell potential decreases. The remaining two graphs are same. Just we have to take change only, whether it may be increase or decrease. Okay, this is by using quinhydrone electrode. Okay, some limitations we have hydrogen electrode. If any oxidizing agents are present, hydrogen undergoes oxidation, and it is a gas electrode, therefore difficult to maintain. Okay, next one, quinhydrone electrode. What is the limitation? pH below 8.5, it gives good results, but if you take pH above 8.5 or 9, okay, then what happens? Hydroquinone. Hydroquinone is an example for weak acid, it undergoes dissociation. Above pH 9 or 8.5, quinhydrone undergoes dissociation. So it gives good results below 8.5. Okay. So next one, by using glass electrode. What is the formula? By using glass electrode, pH is equal to glass electrode. It is an example for what? Ion selective electrode. The formula is E cell plus Eg naught minus 0.242 by 0.059. By using this, we can calculate pH. Eg naught is standard gas electrode potential that depends on nature of glass we are taking. That depends on nature of glass we are taking. Eg naught can be calculated by taking a solution of known pH. If pH is known to us, Eg naught can be calculated. Okay, these are the three equations we have to remember. So pH equations 3 gurtunte migita automatic vachestadandi. Okay, but glass electrode, okay, is not affected by oxidizing agents. It is not affected by oxidizing agent, but it shows alkaline error. It shows alkaline error. If you take high pH, very high pH values, if sodium ions are there, so they may interfere with the H plus ions. They may interfere with the H plus ions. So they show alkaline error. Glass electrode shows alkaline error. Okay. Next we discuss precipitation titration, solubility product. What is the formula for solubility product? The general expression is x power x, y power y, s power x plus y, where x and y are number of cations and anions obtained during dissociation. Stoichiometric numbers of cations and anions. This is the expression for solubility product. It is the product of concentrations of ions present in saturated solution at a given temperature. Okay. So precipitation titration we discussed, and once you see that expression, okay, as concentration during titration, what happens? And concentration of Ag plus ions decreases. Silver nitrate versus KCl. Silver nitrate versus KCl. Okay. So the expression for cell potential ఒకసారి చూడండి 0.558 అంతేనా plus 0.059 log concentration of Ag plus. అంతేనా? Okay. So during titration, what happens to concentration of Ag plus and decreases. So cell potential values also decreases. So E cell versus volume of KCl, if you draw, same graph you will get. The remaining two graphs are same. The remaining two graphs are same. So during titration, what happens? Ag plus ions are replaced by K plus ions. So concentration of Ag plus ions decreases. So cell potential also decreases. Right. Next we discuss redox titration. From redox titration, okay, we discussed iron plus 2 versus cerium plus 3 plus 4 kada. Okay, ammonium ferrous sulfate versus ceric ammonium sulfate. Okay, ammonium ferrous sulfate versus ceric ammonium sulfate. Fe plus 2 versus cerium plus 4. Before end point, what is the expression for cell potential? Before end point, this is the expression for cell potential. E0 Fe3 plus 2 to Fe2 plus 0.059 log concentration of Fe3 plus by Fe2 plus minus 0.242. This is reduction potential of saturated calomel electrode. This is the reduction potential of iron. And Fe3 plus electron gives rise to Fe. To that you may apply Nernst equation. Okay, instead of using minus, we are using plus. That means reactant side by product side will get. So this is the reduction potential of, okay, iron redox electrode, iron redox couple minus reduction potential of saturated calomel. That gives cell potential. So this is before end point. Before equivalence point, cell potential is controlled by which ratio? Fe3 plus 2 to Fe2 plus ratio. Okay, before end point, cell potential is controlled by Fe3 plus 2 to Fe2 plus ratio. So during titration, what happens? Fe2 plus converted to Fe3 plus. So concentration of Fe3 plus increases, Fe2 plus decreases. So therefore, during titration, what happens to cell potential? Increases. During titration, cell potential increases, and at end point, sudden jump is observed. And we also discussed E cell at off equivalence point. At off equivalence point, 50% converted to Fe plus 3, 50% remained as Fe2 plus. So these two concentrations same. So these two gets cancelled. So at off equivalence point, cell potential equal to what? E0 Fe3 plus 2 to Fe2 plus minus 0.242. So that is the expression for cell potential at off equivalence point. 50% converted to Fe3 plus 2 plus, 50% remained as Fe3 plus. So these two concentrations are same, so gets cancelled. After equivalence point, what we get? After end point, another redox couple is formed in the solution. What is another redox couple? Cerium plus 4 comma cerium plus 3. Okay, as long as Fe2 plus present, cerium plus 4 converted to cerium plus 3. Cerium plus 3. After completion of Fe plus 2, in the solution we have what? Both cerium plus 3 and cerium plus 4. Okay, so E cell we get like this. E0 cerium 4 plus 2 to 3 plus same 0.059 log cerium 4 plus by cerium 3 plus minus 0.242. So this is after end point. So cell potential is controlled by cerium plus 4 plus 2 to cerium 3 plus ratio. Okay. Right. Now at equivalence point both will become same. If you add these two, finally we get like this: E cell is equal to E0 Fe3 plus 2 to Fe2 plus E0 cerium 4 plus 2 to 3 plus by 2. We add these two and so this term gets cancelled and minus 0.242. This is at equivalence point or end point. So mainly you remember this and what about cell potential during titration? Increases that, and before end point cell potential is controlled by what? This ratio. After end point cell potential is controlled by this ratio. Okay. Sudden jump is observed due to there is a large difference in the reduction potentials of iron couple and cerium couple. What is the reduction potential of iron couple and what is the reduction potential of iron couple and cerium couple? So there is a large difference between these two values. One is around 700, another one is around 1600. So large difference is there in between reduction potentials of iron couple and cerium couple. That's why sudden jump in the potential is observed at end point. 770. Is it 1610 now? 1610 millivolts. 770 millivolts, 1610 millivolts. So because of large difference, sudden jump is observed at end point. Okay. This is redox titration. So this is about precipitation titrations. Okay. This question given in TSGENCO chemist exam. Okay. So next one we have to see electrolysis and electrolysis. We discussed two cases by using inert electrodes and by using active electrodes. Inert electrodes, platinum or graphite. We may use platinum or graphite or gold as inert electrodes. Again, by using inert electrode, we discussed two cases. What are those two cases? One is molten case, another one is aqueous case. We are taking molten state of electrolyte, aqueous state of electrolyte. So electrolysis, two cases we discussed: inert electrode by using inert electrode, by using active electrode. Inert electrode is the one which do not involve in the electrode reaction. Active electrode is the one which participate in the reaction. Molten state and molten state, is there any competition or no competition? No competition here. For example, Na plus ion is there at cathode, cations move. Na plus ion gives what? Na. For example, copper 2 plus ions are there. What we get? Copper. There is no any competition. Okay. At anode, Cl minus ion is there. For example, we get Cl2 gas. Okay. Here H plus ions are there. We get H2 gas. Okay. If you do electrolysis of HCl and for example, what we get? Hydrogen gas at cathode, chlorine gas at anode. If you have SO4 minus 2, what we get? S2O8 minus 2 if you do electrolysis. Okay. OH minus if you have, for example, sodium hydroxide we are taking, molten sodium hydroxide we are taking. So sodium deposits as sodium ions deposits as sodium at cathode. OH minus ions gives what? O2 gas at anode. OH minus ions gives O2 gas at anode. That is molten state. If you go to aqueous state, there is a competition between cations and water. Cations and water. If you have which cations, water undergoes reduction. Which cations? Lithium, sodium, potassium, calcium, magnesium, aluminum. అంతే ఇంకేమైనా ఉన్నాయా? Lithium, sodium, potassium, calcium, magnesium, aluminum, zinc కూడా కదా? Zinc and H plus, water. If there is a competition between these ions and water, which one undergoes reduction? Water undergoes reduction and gives what? H2 gas. At anode, if there is a competition between what? Fluoride, nitrate and sulfate, nitrate, fluoride, nitrate and sulfate and water, which one undergoes oxidation? Water undergoes oxidation, gives oxygen gas, gives oxygen gas. Otherwise write complete reaction. 2 H2O plus 2 electrons, H2 plus 2 OH minus, H2O plus 2 electrons gives rise to H2 plus 2 OH minus. Here 2H2O gives rise to O2 plus 4H plus 4 electrons. So if water undergoes oxidation, we get oxygen gas. Since once a question given, what is the question given and in JL exam? The solution near the cathode becomes acidic or basic, like that question given. If water undergoes reduction, the solution near the cathode becomes what? Basic. If water undergoes oxidation, the solution near anode becomes acidic. The solution near anode becomes acidic. This is the electrolysis. If there is a competition between these cations and water, water undergoes reduction. If there is a competition between these anions and water, water undergoes oxidation. If you take electrolysis of water, electrolysis of water, what are the products we get? Hydrogen gas and oxygen gas. For the electrolysis of 2 moles of water, how many Faradays are required? How many moles of electrons are involved? 4 moles of electrons are involved. So how many Faradays are required? 4 Faradays are required for electrolysis of how many moles of water? 2 moles of water. So for 2 moles of water, 4 Faradays are required. So if you take 1 mole of water, how many moles of Faradays are required? Sorry, how many Faradays are required? 2 Faradays are required. So to do electrolysis of 2 moles of water, 4 Faradays are required. To do electrolysis of 1 mole of water, 2 Faradays are required. Okay. The ratio of weights of, the ratio of volumes of hydrogen and oxygen obtained is 2:1. Since 2 moles of hydrogen gas, 1 mole of oxygen gas we are getting. So 2:1. That is the ratio of volumes of hydrogen gas and oxygen gas obtained during electrolysis of water. Weights also we can calculate same. Okay, 4 grams. The ratio of weights, if you see, 4:32. 4:32. That means 1:8. So what about the ratio of weights of hydrogen gas and oxygen gas obtained during electrolysis of water? 1:8. 4 grams of hydrogen and 32 grams of oxygen. Okay, so 1:8. Right. Next one we discussed Faraday. Okay, Faraday is nothing but charge carried by 1 mole of electrons. Charge carried by 1 mole of electrons is called 1 Faraday. Its value is 96,500 coulombs. On passing 1 Faraday of electric current, what is the amount of substance deposited in? Always on passing 1 Farad of electric current, always how much amount of substance will be deposited? 1 gram equivalent of substance will be deposited. Whatever may be the substance, whether it may be univalent or bivalent, trivalent, whatever it may be, always how much amount of substance will be deposited? 1 gram equivalent of substance will be deposited. On passing 1 farad of electric current, 1 gram equivalent of substance will be deposited. Okay, number of gram equivalents is equal to what we have? Weight by equivalent weight. So number of gram equivalents is 1. That means if you pass 1 farad of electric current, what is the weight of substance deposited? The weight of substance deposited is nothing but it's a equivalent weight. Okay. For example, if you pass 1 farad of electric current, what is the weight of aluminum deposited? What is the equivalent weight of aluminum? 27 by 3. That means 9 grams. If you pass 1 farad of electric current, 9 grams of aluminum will be deposited. If you pass 1 farad of electric current, what is the weight of copper deposited? Copper 63.5 small atomic weight by 2. That means 31.75 grams. Like that. Okay. So by passing 1 farad of electric current, the weight of substance deposited is nothing but its equivalent weight. So for gases, we may calculate volume. Okay, by passing 1 farad of electric current, the volume of gas evolved is called its equivalent volume. Okay, that we may indicate with VE. By passing 1 farad of electric current, the volume of gas evolved is called a equivalent volume. The weight of substance deposited is equivalent weight. Similarly, the volume of gas evolved is called what? Equivalent volume. What is the equivalent volume of hydrogen and chlorine? And we calculated equivalent volume of hydrogen and chlorine, that is 11.2 liters under STP conditions. Under STP conditions. So if you pass 1 farad of electric current, what is the volume of hydrogen gas or chlorine gas evolved? That is 11.2 liters. What is the volume of oxygen gas evolved? 5.6 liters. Since what is the equivalent weight of oxygen? 8. Equivalent weight of oxygen is 8 and 8 means how many moles of O2? 8 grams means 1 by 4 moles of O2. O2 molar mass is 32 grams. 8 grams means 1 by 4 moles. 1 by 4 moles means we will get 5.6 liters. Okay. Equivalent weight of hydrogen is 1 gram. Okay, 1 gram means how many moles of H2 and half mole of H2. 1 gram. Molar mass of H2 is 2 grams. 1 gram means half mole of H2. Half mole of H2 means we get 11.2 liters. Okay. Right. This is the concept of Faraday. Okay. Next, Faraday's laws we discussed. According to Faraday's first law, the weight of substance deposited at an electrode, the weight of substance deposited at an electrode during electrolysis is directly proportional to what? Quantity of current we are passing in coulombs. Or it may be written as with respect to amperes and time, A into T. If you remove the proportionality, we will get a constant that is called as electrochemical equivalent. That is called electrochemical equivalent. How can you define electrochemical equivalent? If Q is equal to 1 coulomb, then W is equal to Z. That means it is the weight of substance deposited by passing 1 coulomb of electric current. It is the weight of substance deposited by passing 1 coulomb of electric current. That is called electrochemical equivalent Z. What is Z value for aluminum? Okay, if you pass 1 farad, that means 96,500 coulombs, 9 grams of aluminum is deposited. For 96,500 coulombs, 9 grams of aluminum is deposited. Then for 1 coulomb, what is the weight of aluminum deposited? 9 by 96,500. So Z value for copper, 63.5 by 96,500. So Z value is different for different substance. Z value depends on nature of substance. Z value depends on nature of substance. No? Sorry, 31.75, right. 31.75 by 96,500. 31.75 for 96,500 coulombs. Then for 1 coulomb we have to divide with 96,500. So Z value depends on nature of substance. Okay, if Q value is given, then how to calculate weight of substance deposited? Okay, that is EQ by F. That is EQ by F1, or Q may be written as EAT by F. If Q value is given, then how to calculate weight of substance deposited? Okay, some of the equations no need to remember, and simply you can get like this. For 1 Faraday, the weight of substance deposited is equivalent weight. Okay, right? 96,500 coulomb. Then for Q coulombs, what is the weight of substance deposited? What we get? Q by F into E. Q by F into E. Okay, if you pass 1 Faraday of electric current, the weight of substance deposited is E. Then if you pass Q coulombs, what is the weight of substance deposited? EQ by F. Q may be written as A into T, ampere second. 1 coulomb is equal to what? 1 ampere second. Similarly, volume, if you want, in the place of equivalent weight, what we have to substitute? Equivalent volume. In the place of equivalent weight, we have to substitute equivalent volume. If you want to calculate what is the volume of gas evolved, what is the volume of gas evolved? So mainly you remember equivalent volume for these 3 gases, and H2, Cl2 and O2. In our examples, mainly we got those 3, H2, Cl2, O2. According to Faraday's second law, what is Faraday's second law? If you pass same quantity of electric current through different electrolyte solutions, if you pass same quantity of electric current through different electrolytic solutions, the ratio of weights of substance depository is nothing but the ratio of their equivalent weights. The ratio of volumes of gases evolved is equivalent volumes, is in the ratio of their equivalent volumes. One is given in weight, another one is given in volume, and then W1 by V1, that is equal to V2 ankondi. Here E1 by equivalent volume of second. Okay, if both are given in weights, here we get equivalent weights, and if both are given in volumes, we get here equivalent volumes. One is given in weights, another one is given in volumes. So here weight, equivalent weight we have to substitute. Here we want to get in volumes, we have to substitute equivalent volume. Okay. If you pass same quantity of electric current, then what about the ratio of weights of substances deposited at electrodes? Okay, by using this we can calculate. This is Faraday's first law and second law. Okay. Next one, resistance. What is the expression for resistance? Obstruction to flow of current or inverse of conductance is called resistance. The expression is R is equal to rho into L by A. So it is proportional to length of the electrode and inversely proportional to area of cross section of electrode. Okay. If you take short copper wire and long copper wire, which one shows more resistance? Long copper wire shows more resistance. If you take thin copper wire and thick copper wire, okay, which one shows more resistance? Thin copper wire shows more resistance. Okay. Rho is called what? Specific resistance. Rho is called specific resistance or resistivity. Rho is called specific resistance or resistivity. It is the resistance shown by 1 centimeter cube conductor or 1 ml electrolyte solution. If you take L value 1, A value 1 centimeter square, then these two gets cancelled. R becomes equal to rho. If you take L is equal to 1 centimeter, A is equal to 1 centimeter square, then both becomes the same. R is equal to rho. So therefore, this is called as, rho is called as resistance shown by 1 centimeter cube conductor or 1 ml electrolyte solution. Okay. What is the unit for rho? The unit for resistance is ohm. Here centimeter by centimeter square, so we get centimeter. So ohm centimeter. Ohm centimeter in CGS units, ohm meter in SI units. That is the expression for resistance. And conductance, C is equal to 1 by R. If you take inverse of this equation, 1 by rho is called K. 1 by rho is called K into what we get, A by L. K is called as specific conductance or conductivity. Specific conductance or conductivity. That is the conductivity of what? 1 centimeter cube or 1 ml electrolyte solution. Same andi. L by A is also called as what andi? Cell constant. So R is equal to rho into X, cell constant Xn. X is called cell constant, unit is centimeter inverse or meter inverse. Okay. L by A is called what? Cell constant. So R is equal to rho into X. Similarly, here also C is equal to K into L by A is X and A by L we have. So we get by X. So K is equal to cell constant into conductance. Specific conductance is equal to cell constant into conductance. Specific conductance is equal to cell constant into conductance. Okay, K ki unit then. It is the inverse of specific resistance. Okay, that means the unit for rho is ohm centimeter. So 1 by ohm centimeter. That means we get ohm inverse centimeter inverse, or we get Simon centimeter inverse. Simon or millisiemens or microsiemens. Okay, they may give like that. Millisiemens or microsiemens. So Simon centimeter inverse or mho. Ohm inverse also we can write as mho. Okay, or that may be represented by using symbol like this, ohm inverse centimeter inverse. So that is the unit for specific conductance. Okay. So this formula you may remember based on resistance and conductance and its relation with the cell constant. Next one, what is molar conductance andi? Molar conductance. Whatever may be the volume of solution, if it has to possess 1 mole of electrolyte. If the solution contains 1 mole of electrolyte, its conductance is called molar conductance. What is the formula for molar conductance andi? K into volume in ml. So VML of solution conductance is given as K into V in ml. Since K is 1 ml solution conductance, then VML solution conductance is given as K into V. But this VML solution possesses how much electrolyte andi? 1 mole of electrolyte. It has to possess 1 mole of electrolyte. Or this V may be written as, if you take it, it is in ohm inverse centimeter inverse into 1000 by concentration in molarity. Then which units we will get and molar conductance? Ohm inverse centimeter square per mole. If you substitute K value in centimeters, here also we will get in centimeters. And if you substitute K value in meters, here also we will get in meters. If you want to get in meter square, then what is the formula? K in ohm inverse meter inverse by 1000 into concentration in molarity. Ohm inverse meter square per mole. If the data is given in decimeter inverse, ohm inverse decimeter inverse by concentration in molarity. Now we get in ohm inverse decimeter square per mole. So these are the equations we have for molar conductance. The condition is here VML solution contains 1 mole of electrolyte. VML solution has to contain 1 mole of electrolyte. Equivalent conductance andi. Equivalent conductance lambda. So sometimes molar conductance also they are indicating with lambda only. Just by seeing units you may verify whether it is molar conductance or equivalent conductance. So in the case of molar conductance, we have to replace what andi? Concentration in molarity by concentration in So we discussed expressions for molar conductance and equivalent conductance. In the case of equivalent conductance, we have to replace concentration in molarity by concentration in normality. Okay, and what is the relation between molar conductance and equivalent conductance? Mu is equal to lambda into n factor. This is the relation between molar conductance and equivalent conductance. Molar conductance is equal to equivalent conductance into n factor. Okay. So how to calculate n factor we discussed in various methods expressing concentration. Okay. Next one. Effect of dilution on conductance. Effect of dilution on conductance. If you take weak electrolyte or strong electrolyte, you may take weak electrolyte or strong electrolyte, with the dilution, what happens to conductance? With the dilution, molar conductance or equivalent conductance increases. Okay, but what about specific conductance? But specific conductance decreases. So since the number of ions per 1 ml or unit volume decreases, number of ions per unit volume decreases, so specific conductance decreases. If you take in the case of strong electrolytes, with the dilution, if you add solvent, with the dilution, conductance increases. That is due to what? With the dilution, conductance increases due to mobility of ions increases. Is it due to increase in degree of ionization? No, it is not due to degree of ionization, but it is due to what? Mobility of ions. Mobility of ions increases, mu, otherwise you write mobility. Mobility of ions increases, that's why conductance also increases, but finally it reaches a maximum and a constant value, that is called as equivalent conductance or molar conductance at infinite dilution or at zero concentration. So it may be represented like this only. Finally reaches a maximum or constant value. That maximum or constant value is indicated with lambda naught or lambda infinity. Okay. This is in the case of strong electrolytes. What about for weak electrolytes? In the case of weak electrolytes also, with the dilution, what happens to conductance? Increases. The conductance increases due to increase in number of ions. Okay, with the dilution, degree of ionization increases. Degree of ionization alpha increases, and that means number of ions increases. As number of ions or degree of ionization increases, so conductivity increases, but it reaches a maximum value or it doesn't reach maximum value. It doesn't reach a maximum value, so maximum value cannot be, okay, it doesn't reach maximum value, so maximum value cannot be determined experimentally. Maximum value for or lambda infinity of weak electrolytes we cannot determine experimentally, but lambda infinity of weak electrolytes we can determine by using what? Kohlrausch law. Lambda infinity of weak electrolytes we can determine by using Kohlrausch law. If you see graphically, conductance versus square root of concentration, okay, we will get this type of graph for strong electrolytes. Okay, with the dilution means with the decrease in concentration, conductance increases linearly in the case of strong electrolyte, and conductance at zero concentration or at infinite dilution can be obtained by extrapolation. This is lambda infinity or lambda naught. But in the case of weak electrolytes, the conductance increases like this. Okay. So at low concentrations, conductance increases steeply. Nitargan. At low concentrations, conductance increases steeply. So therefore, by extrapolation, can we get lambda infinity, or we cannot get lambda infinity by extrapolation? We cannot get lambda infinity by extrapolation. Okay. So this is in the case of weak electrolytes we get it. Okay, this is the effect of dilution on conductance so lambda infinity we can get from Kohlrausch law. Okay. Next one, Kohlrausch law. Kohlrausch law of independent migration of ions. According to Kohlrausch law, if you take at infinite dilution, where is there any interaction present between the ions or no interaction present between the ions? No interaction present between the ions. Under very, very dilute conditions we are taking such that no interaction present between the ions. Under those conditions, each ion makes a definite contribution towards total conductance irrespective of the other ion present. That means the equivalent conductance of an electrolyte is given as at infinite dilution the sum of the conductances of cation and anion. So every time no need to represent infinity, simply we can write equivalent sum of the equivalent conductances of cation and anion at that dilution. So the conductance shown by cation independent of conductance shown by anion, and the conductance shown by anion is independent of conductance shown by cation. So each ion makes definite contribution towards total conductance. This is equivalent conductance. If you take molar conductance, Nc mu c plus Na mu a. So the difference is, in the case of molar conductance we have to concentrate on number of moles of cations and anions obtained during dissociation. Okay. Stoichiometric numbers also we have to concentrate on. Mu infinity is Nc mu c plus Na mu a. For example, mu infinity of barium chloride, how to write? How many barium ions will get on dissociation? 1. So molar conductance of barium 2 plus at infinite dilution plus how many moles of anions we are getting? 2 moles. So 2 into molar conductance of chloride ions. But if you go to equivalent conductance, what we get? Simply lambda Ba2 plus lambda Cl minus. No need to concentrate on stoichiometric numbers of cations and anions. Next, what are the applications of Kohlrausch law? We can determine what? Lambda infinity of weak electrolyte or mu infinity of weak electrolyte. For example, I want to calculate lambda infinity of AB, and we have to select 3 strong electrolytes. We have to select how many strong electrolytes? 3 strong electrolytes containing A, containing B, and whatever the extra we are getting, that we have to subtract. For example, we are taking like this and AC, BD. Then what about the third one? And we need A and B. What are the extra ions we are getting? And C and D extra ions we are getting. So CD. Okay, so that means lambda infinity of AB can be calculated as what? Lambda infinity of electrolyte containing A and D, that is AC, plus lambda infinity of electrolyte containing B, BD, minus extra, whatever extra we are getting, that is C and D we are getting extra, that we have to subtract. So while we are calculating equivalent conductance, no need to concentrate on stoichiometric numbers only. No need to concentrate on stoichiometric numbers. But while we are calculating mu infinity, we have to calculate on stoichiometric numbers. For that I will give one example. Okay, for example, equivalent conductance of barium hydroxide. I am giving barium chloride. Let us consider sodium hydroxide and sodium chloride. Okay, I am taking electrolyte containing barium, that is barium chloride, electrolyte containing OH minus ions, sodium hydroxide, extra sodium chloride we are getting. So how to calculate it? Lambda infinity of barium chloride plus lambda infinity of NaOH minus lambda infinity of NaCl. Okay, whether we are concentrating on number of moles or we are not concentrating on, not concentrating on number of moles. But if you go to molar conductance, Okay, here how many moles of barium is required? 1 mole of barium. In barium chloride, how many moles of barium is there? 1 mole only. So therefore, mu infinity of barium chloride. Next, here how many moles of hydroxide ions are required? 2 moles. In NaOH, how many moles of hydroxides are there? Only 1 mole. So therefore, 2 into mu infinity of NaOH. How many sodium ions we are getting extra? 2 sodium ions we are getting extra. How many chloride ions we are getting extra? 2 chloride ions we are getting extra. So therefore, we have to subtract 2 moles of NaCl. So like this we have to calculate. Okay. Okay, we have to take number of moles according to our required electrolyte. Okay. Right. So once if you calculate lambda infinity of weak electrolytes, we can calculate its degree of ionization also. Degree of ionization, what is the formula? Lambda C by lambda infinity. So lambda C by lambda infinity, from that we can calculate degree of dissociation. Okay, or degree of ionization. Once if you know degree of ionization, we can calculate acid dissociation constant also. What is the formula? Acid dissociation constant, C alpha square by 1 minus alpha. So once lambda infinity is known to us, we can calculate alpha and acid dissociation constant also. Okay, if alpha is very very small, alpha may be neglected, then we get Ka is equal to C alpha square. This is the first application of Kohlraasch's law. Next, it gives relation between transport number of ion and lambda ion, ionic conductance and transport number of ion. What is that equation? Just you remember that equation. Lambda ion is equal to transport number of ion into lambda infinity of strong electrolyte containing that ion. This relation also we give based on Kohlraasch's law. Lambda ion is equal to transport number of ion into lambda infinity of strong electrolyte containing that ion. For example, lambda H plus we need. So we have to take what? Transport number of H plus into lambda infinity of strong electrolyte containing H plus n. So we may take HCl or H2SO4 or HNO3, whatever it may be. Okay. If you take HCl, we have to substitute here transport number of H plus in HCl. If you take H2SO4, we have to substitute transport number of H plus in H2SO4, like that. Okay. For example, lambda OH minus n. So that is transport number of OH minus into lambda infinity of electrolyte containing OH minus ions. For example, sodium hydroxide or potassium hydroxide, whatever we may consider it, containing OH minus ions. Third application. What is third application? We can calculate solubility of sparingly soluble salts. Solubility, once if you know solubility, we can calculate solubility product also. Okay. So this is the expression we have for solubility product, x power x, y power y, s power x plus y, where x and y are number of cations and anions. So how to get solubility and S? What is the formula? S is equal to K if you take in ohm inverse, centimeter inverse. Total, how many equations we have on this? 6 or 12? 12 equations we have for solubility, right? S is equal to K in ohm inverse, centimeter inverse into 1000 by lambda infinity, that is in ohm inverse centimeter square per mole. If you take, for example, in mole inverse if you take, then what we get? Solubility we get in moles per liter. Okay. If you take ohm inverse, centimeter inverse, 1000 we will get in the numerator, and if you take in meter inverse, we will get 1000 in the denominator. If you take in decimeter inverse, we cannot get 1000, same only. Okay. Like that we will get 3 equations. And another one is, if you give solubility in grams per liter, what we have to do? We have to multiply with what? Molecular weight. Then we get in grams per liter. If you multiply with molecular weight, then we get in grams per liter. So if you take in meter inverse, and ohm inverse, meter inverse by 1000 into lambda infinity ohm inverse centimeter square per mole. Okay, then we get in moles per liter. If you take in decimeter inverse and ohm inverse, decimeter inverse, 1000 we cannot get. Lambda infinity in ohm inverse centimeter square. This is meter square, sorry, meter square. Here ohm inverse decimeter square per mole. We get in moles per liter. To convert moles per liter to grams per liter, what we have to do? We have to multiply with the molecular weight. If you want to get in gram equivalents per liter, what we have to do? To get in gram equivalents per liter, solubility in gram equivalents per liter, in the place of lambda infinity in ohm inverse meter square per mole, what we have to take? Lambda infinity in ohm inverse meter square gram equivalent inverse. Okay, mole inverse we have to replace by what? Gram equivalent inverse. Okay, mole inverse we have to replace with the gram equivalent inverse. And if you want to get in grams per liter, if you want to get solubility in grams per liter, okay, then molecular weight we have to replace by what? Equivalent weight. Molecular weight we have to replace by equivalent weight. Okay, after getting in gram equivalents per liter, if we want to convert into grams per liter. To convert into grams per liter, we have to multiply with the molecular weight. In the place of, equivalent weight. In the place of molecular weight, we get equivalent weight. Like the total 12 equations we will get. Okay, for example, I have given data in ohm inverse decimeter square gram equivalent inverse. Okay, then S is equal to what we get? K in ohm inverse decimeter inverse by lambda infinity ohm inverse decimeter square gram equivalent inverse. Then what we get here? Moles per liter or gram equivalents per liter? Gram equivalents per liter. Here we will get gram equivalents per liter. Mole inverse I have replaced by gram equivalent inverse. So here we will get in gram equivalents per liter. So after that, if you want to convert into grams per liter, we have to multiply with what? Equivalent weight. We have to multiply with the equivalent weight. Okay, right, this is solubility. Once you get solubility product we can calculate by using this equation. These are the applications of Kohlrausch law. Okay, తర్వాత ఇంకేముంది అంతే కదా. నెక్స్ట్ డి బై హెకెల్ థియరీగా మనం డిస్కస్ చేసింది. డి బై హెకెల్ థియరీ. ఫ్రమ్ దట్ డి బై హెకెల్ థియరీ, this is the main we are getting. So de Bhayekal theory considered what? Formation of ionic atmosphere. Okay, at high concentrations why mobility of ions is low only. At high concentrations two effects are present. What are those two effects only? One is asymmetric effect or relaxation effect, another one is electrophoretic effect. At high concentrations, because of these two effects, what about the mobility of ions? Okay, because of these two effects, mobility of ions decreases at high concentrations. So conductivity values also low. Conductivity values are low at high concentrations. These two effects are called what? Interionic effects and interionic interactions. Because of interionic interactions, okay, or interionic attractions, these two effects are observed. Ionic atmosphere, that means what? Positive ion is surrounded by negative ions, negative ion is surrounded by positive ions. Okay. So by taking into consideration of asymmetric effect, electrophoretic effect, and the third one, another effect is considered by de Bhayekal theory. What is that? Viscous effect. By taking into consideration of these three effects, they proposed an equation between molar conductance or equivalent conductance of an electrolyte and concentration. How conductance changes with the concentration. What is that equation? Lambda is equal to lambda infinity or lambda naught A plus B lambda infinity into root C. Lambda is equal to lambda infinity minus of a plus b lambda infinity root c. So repeatedly previously questions given from this equation. It is in the form of what? Y is equal to c plus mx. So by taking a plot of lambda versus root c, from intercept we can calculate what? Lambda infinity or lambda naught, okay, of strong electrolyte. One of the assumptions in de Baekel theory is electrolyte undergoes 100% dissociation at all concentrations. So that may be applicable in the case of strong electrolytes only. Okay. Okay, right. So if you plot a graph lambda versus root c, you will get a straight line with negative slope. If you extrapolate up to 0 concentration, we will get what? Lambda infinity. If you extrapolate up to 0 concentration, we get lambda infinity. One of the limitations in the de Baekel theory is experimental values are lower than whatever we are getting based on de Baekel theory. So this is the expression based on de Baekel theory, but experimentally we are getting like this. Experimental conductivity values are lower than whatever we are getting based on de Baekel theory, since de Baekel not considered what? De Baekel not considered formation of ion pairs, ion association, okay, or formation of ion doublets, that is not considered by de Baekel theory. Whenever ion pairs formation takes place, then what about number of ions? And decreases. Number of ions decreases, so conductivity also decreases. So that is not considered by de Baekel theory, but that is considered by what? Bejerum's theory. According to Bejerum's theory, when ion association takes place, and if R value is less than or equal to R minimum, then only ion association takes place. If R value is less than or equal to R minimum, then only ion association. If the distance between the ions is less than R minimum, then only ion association takes place. But what is the expression for R minimum? You remember this only. Z plus Z minus epsilon square by 2d kT. That means as charges on the ions increases, what about R minimum? Increases. And as dielectric constant of the medium decreases, R minimum increases. Whenever R minimum increases, more number of ions involved in the ion association or less number of ions? More number of ions involved in the ion association. So extent of ion association increases. Extent of ion association increases. So that is the conclusion from Bejerum's theory. And according to Bejerum's theory, what is the expression we got for ion association constant? And ion association constant under dilute conditions, we got theta by C. Ion association constant expression is theta by C, where theta is the fraction of ions associated. Fraction of ions associated. Mainly from ion association, this is important. And when extent of ion association is high, if valences on the ions is high or lower is the dielectric constant, extent of ion association is high. Next, this is the expression for ion association constant under dilute conditions. Next one, we have to remember de Baekel limiting law. This is important for all competitive exams. De Baekel limiting law. It gives relation between what? Mean ionic activity coefficient and ionic strength. Mean ionic activity coefficient and ionic strength. So which is in the form of y is equal to mx. So if you take log gamma plus or minus versus root I, slope is equal to minus 0.509 z plus z minus. Or if you take minus log gamma plus or minus versus root I, what we get? And slope plus 0.509 z plus z minus. If you take log gamma minus log gamma plus or minus versus root I, if you take log gamma plus or minus versus root I, slope is minus 0.509 z plus z minus root I. So from that, if you plot a graph between log gamma plus or minus versus root I, slope depends on what? And slope depends on what? Valence is present on the ions. As valence is present on the ions increases, we get more negative slope. We get more negative slope. No intercept, we get straight line passing through origin. So we will get slopes like this, and for 1:1 electrolyte, 1:2 and 1:3 electrolytes. Okay, this 1:1 means charge valence is on the cation is 1, valence on the anion is also 1, NaCl, KCl, like that. 1:2. For example, 1:2 or 2:1 and barium chloride or magnesium chloride. Okay, 1:2 or 2:1 electrolytes, you will get like that. Okay. So as charge numbers increases, okay, we get more negative slope. And if you take minus log gamma plus or minus versus root I, we will get straight line passing through origin with a positive slope. And okay, and like this we will get. And if you take minus log gamma plus or minus versus root I. Okay. The limitations, what are the limitations in de-Broglie limiting law? Why it is called a limiting law? And it is applicable to dilute solutions only. Okay, in this theory, ions are assumed as what? And point charges. Ions are assumed as point charges. The size occupied by ions is negligible. So that is a good approximation only when if you take dilute solutions. So this is applicable to only dilute solutions. Okay, next one. Okay, the nature of plot is same for KCl, NaCl, LaCl according to de-Broglie limiting law. Here charge number on cation and anion is 1, 1. Here also 1, 1. Here also 1, 1. That means nature of plot is same for KCl, NaCl, LaCl. Okay, according to de-Broglie limiting law, but experimentally it is different for KCl, NaCl and LiCl. Experimentally it is observed that we are getting different plot for different plot for KCl, NaCl, LiCl. Our nature of plot depends on nature of substance also. Nature of plot depends on nature of substance also, that is not considered by de-Broglie limiting law. Okay. Next, experimentally it is observed that the log gamma plus or minus value starts rising after reaching a minimum value. So this we are getting experimentally at high concentrations. So why again it starts rising, that is not explained by de-Broglie limiting law. These are some limitations we have de-Broglie limiting law. That equation important only. Log gamma plus or minus is equal to minus 0.509 z plus z minus root I. Repeatedly they are giving questions. Okay, or this 0.509 is indicated as A. A is a constant. This constant depends on what? And temperature and nature of solvent. If you take specially temperature 25 degrees centigrade and water solvent, then we get 0.509. Okay, minus A z plus z minus root I. Okay, actual expression. If you take specially 25 degrees centigrade and temperature water solvent, then we get A value 0.509. And I value, what is the expression for ionic strength? Half into summation I Ci Zi square. If you take 1:1 electrolyte, what is the relation between I and concentration? I is equal to concentration. If you take 1:2 or 2:1 electrolyte, I is equal to what? 3m. 2:2 electrolytes, 4m. 1:3 electrolytes, the relation between ionic strength and concentration is 6m. So this is the relation between ionic strength and concentration for 1:1, 1:2, 2:2 and 1:3 or 3:1 electrolytes. Okay. Right. Next, that concept you may remember, and electrode polarization concept. How to prevent electrode polarization, and what are the how to reduce electrode polarization, and how to reduce electrode polarization. Electrode polarization can be reduced by what? One is continuous stirring, right, by using depolarizers or oxidants. So generally used oxidant is MnO2, chromic acid, and HNO3 also we have, but HNO3 and chromic acid are hazardous in nature, so MnO2 is widely used depolarizer. Next one, by increasing temperature and by using rough electrodes or smooth electrodes. Rough electrodes. So this is electrode polarization, and how to remove electrode polarization. When an electrode is said to be polarized, and if it is covered by a gas, if an electrode is covered by a gas, then we say that electrode is polarized. What is the example for polarizable electrode? What is the example for polarizable electrode? The example is platinum, lead, next dropping mercury electrode. Mainly you remember this dropping mercury electrode is an example for polarizable electrode that is used in polarography technique. What are the examples for non-polarizable electrodes? Right, reference electrodes. Reference electrodes you may remember. Reference electrodes are examples for non-polarizable electrodes. Okay, electrode polarization can be reduced by continuous stirring, by using depolarizers, by increasing temperature, and by taking rough electrodes. Okay, if you take smooth electrodes, electrode polarization is high. Next one, okay, over potential. Ante kadandi. Over potential is nothing but the difference between what? Difference between actual value and theoretical value. The difference between actual value and theoretical value to start reverse reaction. To start reverse reaction, that is called over potential. Difference between actual value and theoretical value to start reverse reaction is called over potential. To start reverse reaction or to deposit ions. To deposit ions. Simply whatever the excess potential required than expected, and whatever the excess potential required than expected, that is called over potential or over voltage. Okay, that may be observed due to concentration gradient also. Okay, as fast as ions present at electrode surface, if they are deposited on the electrode, okay, with the same speed, if ions are not moving from bulk to the electrode surface, in such cases also we can observe over potential. Such over potential is called concentration over potential. What is the formula for concentration over potential? RT by NF ln CE by CS, where CE is the concentration of ions at electrode surface, concentration of ions in bulk solution. If concentrations are same, no concentration gradient is developed. In such case, over potential is not observed. Concentration over potential is not observed. Okay. And we discussed some applications of over potential that you may verify once. Okay, hydrogen deuterium separation. Hydrogen deuterium separation. Next, if you take aqueous NaCl, actually water undergo oxidation at anode, but instead of water undergoing oxidation at anode, chlorine undergoes oxidation to give chlorine gas. That is due to over voltage of O2. Over voltage of O2, H2O cannot undergo oxidation, but Cl minus ions undergo oxidation. Even though oxidation potential of water is more compared to chloride ions, water cannot undergo oxidation. Why Cl minus ions undergo oxidation? And if water undergoes oxidation, which gas is evolved? Oxygen gas is evolved, but oxygen over voltage is high. That's why oxygen cannot be evolved. In polarography also, what is the advantage of over voltage in polarography? Over voltage of hydrogen on dropping mercury electrode is high. hydrogen over voltage is high on dropping mercury electrode, otherwise you write like that. Hydrogen over voltage on dropping mercury electrode is high. That's why whether hydrogen interfere with the deposition of other ions or it cannot interfere. It cannot interfere with the deposition of other ions. Okay. So while we are doing polarography technique, whether hydrogen gas interference is observed or we cannot observe. Hydrogen gas interference is not observed, since to deposit hydrogen gas on dropping mercury electrode, excess potential is required. Right. Okay. Mainly you remember those points. So far no questions given from electrode polarization and over potential concept, but this time PG level mentioned, so we may expect questions only. So once you refer these points, right, with this electrochemistry completed. Okay. So first you refer regular notes 3-4 times, after that you follow this video only. Okay. So then for quick revision it is useful. Okay. So first you read 3-4 times our regular notes only, after that only you follow this information. Okay. So no class, right? So organic class also not there. So tomorrow timings are 5 to 8:30 organic andi, only organic, 5 to 8:30 p.m. organic class you have. So I will try to put next exam on solid state chemistry andi, after the completion of thermodynamics. Okay, thermodynamics up to entropy completed. Next exam from the remaining portion of thermodynamics, and remaining portion means third law, Gibbs free energy, Maxwell relations, Van 't Hoff equation, Clapeyron equation, and from part 1 also overall thermodynamics andi. Okay, the next exam is on total thermodynamics. Next exam will be on total thermodynamics andi. After completion of thermodynamics I will put exam on solid state chemistries. So later after completion of that exam we will discuss overall solid state chemistry also once. Okay, right. Thank you, Andy. Right.